Sir, we'll start slowly. People would reach. Okay, sir.
Okay, so I'll start.
No, let me introduce formally
Okay,
1 minute, and then you can start, sir. Right, sir?
okay.
Okay. Good afternoon, one and all. This is Rajshekhar from Geetam University, Bangalore campus. Today we have Dr. Avinash Tiwari from Forschungszentrum Jülich, Peter Grunberg Institute, Germany. Dr. Avinash Tiwari is now currently working as a research associate at this Peter Grunberg Institute, Germany. So let me tell a few words about the Tiwari, sir. So Dr. Tiwari has completed his PhD from Norwegian University of Science and Technology in the area of engineering design and materials, Norway, in 2018. He has completed his MTech from IIT Delhi in the area of polymer technology in 2012. Sir has also completed his graduation in the area of polymer technology only. So Dr. Tiwari's research areas include polymer composites, contact mechanics, elastomer tribology, adhesion, and sealing technology. These are a few to mention. Tiwari is working on many more areas related to tribology. These are some of these areas to mention. And Dr. Tiwari has authored more than 20 research articles are being published in various renowned international journals. And Tiwari has also delivered talks at various international level and national level conferences in his research area. So today we are very glad to have Dr. Tiwari for this afternoon session. Dr. Tiwari is going to present a talk on polymer tribology with a focus on rubber friction. So we are very happy to have you here, sir. And once again, I would like to extend a warm welcome from Geetam University and Department of Mechanical Engineering and the management of Geetam University. Welcome to this Geetam online program, sir. Thank you very much, sir, Dr. Avinash Tiwari. Now you may please share your presentation, sir. You can start the lecture, sir.
Yes,
Thank you.
thank you for inviting me. And so the today's talk will be on polymer tribology, as but I will be focusing more on rubber friction. So I will so yeah. So the outline of my presentation will be as follows. So I will talk briefly about polymers. Then I will talk about important properties of polymers that should be considered for any application, which are very important. And then I will talk about rubbers, because the focus of this talk is rubbers. And then I will talk briefly about the viscoelastic response of rubbers. Then I will come to tribology. I will motivate the tribology through introduction of surface roughness, and then I will move towards Person's theory of contact mechanics, which is the state of art in contact mechanics. And then I will tell some experimental and theoretical results on rubber friction on a very basic level. Then I will talk about two applications. One is statics on static ceilings, and then I will talk about some challenges in dynamic sealing systems. So polymers. So what are polymers? So polymers are nothing but you have monomers and then you polymerize them to form polymers. So polymer are basically monomers polymerized to form long chains, and polymers have high molecular weight. Polymer is a large molecule made up of small building blocks, and monomers are the building blocks. Like you have a unit cell and then crystals that you form out of the unit cell. So it's like the same thing, but in chemistry, we say it's building blocks are monomers, and then we polymerize them to form a polymer. And then there are different kinds of polymer, homopolymer and copolymer, depending on if the monomers are same or different. If there are different monomers that are used to polymerize, then we form a copolymer. And if we use the same monomer, uh, if we use the same monomer, we make a homopolymer. And blend is a mixture of two polymers. So how to classifying polymers. So basically, polymers are classified into three categories. thermoplastics, thermosets, and rubbers or elastomers. Basically, thermosets and rubbers or elastomers, they are 3D networks which are covalently cross-linked, and they get cross-linked when you applied heat and curing agents into them. Thermoplastics are long chain polymers which are bound together by physical entanglements. This means that the chains are just having van der Waals or dispersive forces between them, and they come together and form domains, solid domains, crystalline domains, and amorphous domains. So thermoplastics can be of amorphous nature and semi-crystalline nature. Thermosets and rubber elastomers are amorphous materials. There are some, so examples of thermoplastics would be polyethylene, polypropylene that you use in your daily application. Polyether ether ketone is an engineering thermoplastics, and which is used in engineering applications. Now people are trying to use polyether ether ketone in bearing applications. They want to make bearing cages out of polyether ether ketone. And the thermosets, that people make composites out of thermosets. So they use epoxy resin, phenolic resin, polyester resin. So they embed many fibers and they make boats, yachts out of these materials. And then I will talk about elastomers in coming slides in more detail. So what makes polymer unique? What properties are more important which for an application? So polymers are viscoelastic solids. That is, they behave both as elastic solid and viscous liquid. And if it behaves as an elastic solid or viscous liquid is decided by what we call as de Boer number. So de Boer number is defined as the relaxation time divided by the observation time. If your time of observation is very large, this means your de Boer number is much less than 1, and you will see that there is everything will flow. So there are instances in Bible or whatever. They say that mountains flowed before the Lord. So because the time of observation is so high for him, everything flows. And then there is elastic behavior. Here, the relaxation time is much higher than the observation time, and then you have an elastic behavior. And viscoelastic is in between these two behaviors. And polymer properties depend on temperature, time, and applied stress and strain. I will discuss this in further in the coming slides. Polymers properties properties of polymers can be tailored for any particular applications. You can compound the polymers with additives, fillers, and you can make the polymer suitable for any application, taking into account limitations of the polymers. And there are infinite designing possibilities with polymers. You can nowadays people use 3D printing, and they can make a lot of beautiful things out of them, and there are many applications with polymers. There are the number of polymers are increasing day by day. They are discovering many polymers. So now I will talk about the most important property of any polymer. It's called glass transition temperature, and then I will discuss about time temperature superposition. So glass transition temperature is the temperature at which there is a temperature at which the polymer chains start to have this segment. There is onset of segmental mobility in the polymers. That is, they start to move. If you decrease the temperature, the segmental mobility will decrease, and if you increase the temperature, temperature, the segmental mobility will increase. So there is a freezing of segmental mobility, and then there is unfreezing of segmental mobility. The point at which this happens is 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 called Tg of the polymer. That is the glass transition temperature of the polymer. So, and the segmental mobility depends on the free volume that is available for the polymer chain segments to move. So when you decrease the temperature, the free volume in the polymer is it starts to decrease, the polymer starts to contract, and then the free volume is less, so polymer chains cannot move, and then they behave as elastic solids. You see here that there is, if this is a shear modulus versus temperature curve, and you see as you lower temperature, then you have an elastic solid that is very high modulus. When you start increasing the temperature, there is a transition region, and then you have at this point the mobility of the there is onset of polymer, there is onset of segmental mobility within polymer chains, and then the modulus starts decreasing, and the midpoint of this transition region from glassy to rubbery state here is what we call as Tg, that is glass transition temperature. So you can measure glass transition temperature by different methods, like dynamic mechanical analysis, differential calorimetry, dilatometry. These I mentioned some of the glass transition temperatures of common polymers, and some of them are some elastomers. So polyisoprene is a natural rubber, and its glass transition temperature is -73. This means below -73, the glass will polyisoprene or natural rubber will start behaving like an elastic solid. This means at the Tg here is -73. So below this, it will start behaving as elastic solid, and above that, it will behave as rubbery material. High density polyethylene has a Tg of -115, because you will see that polyethylene is still a hard solid at room temperature. This is because of its semi-crystalline nature. And then there are different polymers with their TGs given. So and their melting points are also given here. So the most in polymers, there is what we call as time temperature superposition principle. Here we say in time temperature superposition, frequency and temperature are equivalent. In the sense, if you measure a property at for example, if you measure shear modulus as a function of frequency at different temperatures, what you can do is you can take a reference temperature, say T0, and then you keep it as it is, but then you can start moving the segments which are measured at T1 and T2 as a to T1 and T2, and then you can form a smooth master curve. So the objective of forming a master curve is to extend the range of your measurement. Suppose if you want to predict, but it is to basically save time in property prediction. And so if you want to say you want to predict storage modulus at very high frequencies, but with the data here you cannot predict. But with time temperature superposition principle, you can shift these curves, and you can predict the data, predict storage modulus at very high frequency and also at low frequency. So this extends the range of your prediction, time temperature superposition principle. And the amount by which you shift these curves is what we call as shift factor. So here at temperature T0, it was acting as a reference temperature. When this T1, you are moving to a certain distance, a certain horizontal distance, and then that distance is what we call a shift factor. So segment, each segment here has to move a certain distance in order to overlap with the reference temperature. So you can have a function which is what we call a shift factor function, which is given by this WLF equation. This is called William Landau's Flory equation, in which they and which is valid from temperature ranges from TG to TG plus 100. So here is an example of master curves which were made using time temperature superposition principle. So you can see that you can, with time temperature superposition principle, you can extend the range of your you can extend the range of your property prediction. And here are the shift factors which were used to make the shift curves, master curves, sorry. So here are shift factors which were used for making these master curves, uh, and each material here, they have their own WLF fit constants. So I will talk now about rubber and its viscoelastic response. So rubbers and elastomers, these, as I have told you, these are 3D networks which are covalently cross-linked. And this covalent crosslinks is the most important thing in elastomers. If there are no covalent crosslinks in the elastomers or rubbers, then they'll start to flow. So these covalent crosslinks is what gives them their properties of high reversible elasticity, or what we call as hyperelasticity. And we can modify the properties of elastomers by incorporating different curing agents, different fillers. I will come to that in the coming slides. So rubbers are both viscoelastic and hyperelastic. So in the sense, you see that if you measure the modulus as a function of temperature, you see that there are 5 regions here. There is a glassy region, there is a rubbery plateau, there is a rubbery flow region, and then there's a liquid flow. So when you increase the temperature there is at this region, this is what I told you, this is a glass transition temperature region. This is where the modulus drops uh, by 3 orders of magnitude. So typically the glassy region, the modulus will be around 1 gigapascal. But when you start increasing the temperature, the rubbery plateau, when it comes to the rubbery plateau, the glass transition, the modulus will be around 1 megapascal. So there are order of magnitude reduction in the properties of the material. So you understand that if you increase the temperature in the elastomer, then your properties of modulus change. And if you measure a stress strain curve, you see that elastomers are non-linear viscoelastic materials. So if it was a linear curve, then you will be seeing a straight line here, but it's non-linear. So there is no linear relationship between stress and strain. And as I told you, the crosslinks in elastomers is what imparts high reversible elasticity. Otherwise, if there is no crosslinks, the elastomers will start to flow. So viscoelasticity, time and temperature. I will talk about the time and temperature behavior now. So see, I will again repeat a bit. So to reinforce this concept. So temperature behavior. If you plot the shear modulus or shear storage modulus or tensile storage modulus as a function of temperature, you will see the modulus will start decreasing, and then from the glassy state to the rubbery state, you will have change in modulus at the glass transition. So the maximum of tan delta here is what we call glass transition temperature. So this is the mid region of this transition. If you take a rubber band at room temperature, the rubber band will be very elastic. You can extend it a lot. So the rubber band is in the rubbery region. But when you have a rubber band and when you cool it down to liquid nitrogen temperature, then you cannot extend. The rubber band is now brittle. It is a glassy solid, and it has a very high modulus in order in few few gigapascal. So now, if you look at the frequency response of elastomers, you see that with increasing frequency, you will have, uh, with increasing frequency, is just the opposite of your temperature behavior. With so high frequency corresponds to low temperatures, and low frequency responds corresponds to high temperatures. So if you know about silly putty, if this silly putty is a material, if you stretch very quickly, it behaves like a solid. But if you stretch slow, so this means that if you stretch quickly, it does not have time, and then it will behave like a solid. But if you stretch it slowly, then it will behave like a rubbery, like a viscous fluid. So it will start flowing. And these properties are in the linear region, in the linear viscoelastic region. These properties are valid at linear viscoelastic region. So in order to make any rubber useful for an application, you need to compound it with different ingredients. So there are many different ingredients that you can compound them with. You can mix with into this rubbers. Rubbers can be natural, nitrile butadiene rubber, or fluoroelastomers. You can use them, and you can use them as a base material, and then you can start adding fillers, anti-degradants, plasticizers, and cure systems to modify their properties for your application. So these are different ways by which you can modify rubber's property to get the elastic modulus response you want, or the loss behavior you want. So for me, and these components, for example, fillers, these components, uh, there are many different length scales involved in making a rubber composites. So you see, fillers can be of many types: graphite, silica, carbon black. Their size varies from sub nanometer to hundreds of nanometers. So, so the main point of this slide is to show you that in making any rubbers used for a particular application, fillers of different dimensions are used. And if you and after, so what you basically do, this is the main process. So you take different additives, that is antioxidants, plasticizers, fillers, processing aids, and curing agents, and then you mix them. You mix rubber with these additives into a mixer. Here we call, in the rubber industry, it's called as a Banbury mixer, internal mixer. And then you also add the curing agent here. Then you get a mixed compound. Then you mold the compound by compression molding or transfer molding, and then after that you post cure the compound, and you get products. And products can be tires, seals, rubber plugs in syringes. Seals can be of dynamics, can be dynamic seals, static seals. So you can, from the basic raw material, you can make, through rubber compounding, material for engineering application. Now I will talk about the main topic of our talk, main topic, which is tribology. So tribology, as you would by now all be knowing, is a science in which you study the how surfaces interact with each other in relative motion. So it involves friction, adhesion, and contact mechanics. and contact mechanics is very important, because if you have contact mechanics is very important, because two surfaces, when they come in contact, they form contact. So the mechanics of contact is very important. Then lubrication and wear. So these comprise the study of tribology. For example, if you take a car, you have different avenues where you are using the concepts of tribology. For example, you use lubrication in engine and gear, and there are many seals which you don't want leakage in different seals. There are many seals. There are rotary lip seals, there are O-rings, which you don't want them to leak. Uh, and then there is these tires in cars which have interaction between tire and road. Then there is brake friction composites, which are used in cars. You would have listened to a talk by Dr. Tej Singh, in which he would be talking. He would have talked about brake friction composites, and then rubber wiper plates for removing water. So these are all involving contacts, and there is a relative motion between these contacts, and this is where tribology comes into picture. It is estimated that if you are ignoring tribology, you are losing a lot of money. So our ancestors, which were hominoid, more than 400,000 years ago, they somehow by trial and error came to know about the concepts of tribology. Here you see these people, they are using frictional heating. So they are rubbing so they are rubbing two surfaces together to generate frictional heating, and then the discovery of fire and stuff. So tribology is very fundamental science. So Leonardo da Vinci was one of the pioneers in starting tribological studies. In Leonardo da Vinci's time, there was no concept of force. He used blocks, and then he were able to formulate his crude laws. But for example, here you see that there are two blocks. They have different apparent area of contact. This block has a smaller apparent area of contact, and this block has a bigger apparent area of contact. But the weight or the mass of them is the same. So the frictional force that is required is also the same. But people will think that the frictional force in both the blocks will be different. But as the frictional force is dependent on the area of real contact, the area of real contact and the area of contact depends on the normal load. So that is why we see that these both blocks will start to move at the same frictional force. Because of surface roughness, what happens is there is a surface roughness between these two surfaces, and here the contact pressure, the normal contact pressure because of surface roughness is higher. But here because the contact pressure in this case is a bit lower. There is also surface roughness there, but the contact pressure is a bit lower. So they even out, and then there is a proportionality between the friction force and the area of real contact. So tribology is all about surface interactions. Wolfgang Pauli, one of the great physicists, he said, God created the volume, but the surface was invented by the devil. But surfaces are very important, and interaction between solids usually occurs at surfaces where they contact each other. So I have already told you that there, in the previous examples, that there in cars, uh, uh, they have wiper blades. They want to remove water from the windscreen, and then you use wiper blades. Here you have syringe. In the syringe application, what happens is you have this rubber plug against the barrel, and the problem is that if there the break loose friction is very high, uh, then what happens is, if you want to inject some fluid into the patient, it's very difficult to inject fluid if the break loose friction is very high. And so in syringe application, we want a stable friction with stable sliding friction and low break loose friction. This is a challenge, and for this you have to optimize many different parameters. And here you have tire and road, which uh, uh, which is uh, y- uh, which is a typical tribological situation. I will talk about that more in coming slides. Then in humans, you have the synovial joints. This is an area of biotribology. And then you have a contact between this contact lens and your eyes. This is also a biotribological area, uh, active area. And then this is all. So there are geckos which can move along vertical walls, uh, because they have some hierarchical structures. Nature have evolved them to have these hierarchical structures which can help them to move on vertical walls. This is also an interesting area of tribology. This is also area of biotribology. So if you take a steel block, uh, two steel blocks, both are steel blocks, and because of surface roughness, you will see that the area of real contact is very less. If you calculate area of real contact for these steel block, which is 10 centimeter wide, the area of real contact will be approximately 0.01 square millimeters. This is for elastically hard solids. But if you take a smooth rubber, for example, tire application, you will see that the area of contact will be approximately 1 square centimeter. And if you accelerate your car, you sometimes see these smoke coming out, and that this is because that uh, at such a small contact, such a small area, in such a small area of contact, if you accelerate, there is high frictional heating, which can lead to disintegration of your rubber, aging of your rubber. There are so many which can destroy your tire also. So this is also a challenge to make tires which don't disintegrate. Now I will talk about the main topic of this whole talk. It's surface roughness, and I will briefly discuss about Parsons theory of contact mechanics. So all surfaces have surface roughness. In any engineering application you take, even the in ball bearings, which you see for with the naked eye, you will see ball bearing, the balls will be very uh, very they are very smooth and very shiny, and it seems that there is no surface roughness there. But if you start magnifying the surface, you will see that you have surface roughness. And you further magnify, if you start further magnifying at the top of this asperity, then you will see a further surface roughness. And this you can do until up till atomistic level. So there are at least from centimeter to nanometer level, you have 7 decades in length scales. So if you want to do numerical computation for a tribological system, so you have 7 decades of length scale in x direction, 7 in y, 7 in z. So there are 21 different length scales. This means 21 different length scale, 21 different length scales, and different and many degrees of freedom. And it's impossible for any numerical computation or any computer in the world to solve this problem. So we need an analytical approach, and that analytical approach uh, is what Dr. Person has proposed. Professor Person has proposed a new contact mechanics, which is a multi-scale contact mechanics. So you would have already learned about surface roughness power spectrum from maybe Professor Bobji's lecture. I will just review it here. So if you measure surface roughness, suppose using a stylus instrument, you can decompose this surface roughness into a into a sum of sinus and cosinus profiles having a height amplitude and a wavelength. And then you can plot the square of the height amplitude versus the wave number. Wave number is related to the wave number uh, like this. The wave number is equal to 2 pi upon the wavelength. So if you plot the square of the height amplitude with the wave number, you will form what we call as power spectrum. This power spectrum so this power spectrum contains all the information that is needed to know about a surface and its roughness characteristic. So the region between Q0 and QR is what we call is the region where it's called roll-off region. Here uh, the height amplitude is the same. If you even change your wave number, it will not change. So this is the wave roll-off region. So, and the region between the QR and Q1, this is the most important region. This is where the power law is followed, where you will see that there is and the slope of this curve between QR and Q1, the slope of this line is an indication of fractal dimension. And typically for surfaces, you will have the power spectrum as indicated here. And this straight line, the power law relation here, is basically an indication of self-affine fractal surfaces. I will talk about fractal dimension. So suppose you have suppose you have a surface roughness that you have got, and if you magnify this surface, you will have a surface similar to that, but having higher height amplitude. So this means in this case, the fractal dimension will be more than 2. But if this profile has nearly the same height amplitude as the previous profile, then you have a fractal dimension of approximately 2. So here I show surface roughness power spectrum of different surfaces. Here it's asphalt, here it's grinded steel, here it's a human wrist skin, and here it's a peeled adhesive tape. You can see that there is a power law relationship here, this slope here. And this slope is in all of different in all of the different surfaces. Here you have this slope, and this slope gives you an Hurst component, and from Hurst component you can calculate what we call as fractal dimension. And you can see the fractal dimension for all the surfaces lies between 2.2 to 2.3. And this fractal dimension of 2.2 is the most is, we can say, naturally it's for many naturally occurring surfaces, the fractal dimension is 2.2. And you can see here, for example, grinded steel, you can make you can measure you can measure your surface roughness with different instruments. Say here it was done by 1D line scan, 2D AFM, and 2D scanning tunneling microscopy, but then they basically overlap with each other to form a complete power spectrum. ranging from a centimeter to a nanometer. So depending on the length scale you're interested in, uh, you can use different techniques to characterize your surface. And these surface roughness power spectrum is is very important to characterize the surface roughness of your materials. It has all the information that is needed for doing contact mechanical calculation and related predictions. So now I come to contact mechanics. Uh, so contact mechanics basically starts with Hertz. Hertz basically was known for his work in electromagnetism, but for tribologists know him because he gave a relation because he gave a relation between contact area and the force between two spheres which are squeezed together. So according to Hertz, the area of real contact when two elastic spheres are squeezed together is a non-linear relationship between a so area of real contact depends on the normal load uh, to the power 2/3. uh, I will now introduce about Person's theory, various contact mechanics theories. So if you take two surfaces which are randomly rough surfaces, you will form contact like this shown here, and when you squeeze them you will have areas where you make contact and the areas where you don't make contact. So the areas that you make contact, and when you count all the areas where you make contact, you can find the area of real contact from them. And then then you can also find interfacial separation, the average interfacial separation, the non-contact areas, which are very important in certain sealing applications. For example, there is a static o-ring which is in contact with a surface. Then the non-contact region is the region which decides where the leakage will happen, how the leakage will happen, and whether the leakage will happen or not. So Hertz in 1882, what he did, he took a elastic solid and he compressed it against, in his theory, he compressed it against a rigid solid having spherical bumps which are of equal radius. And each radius here, each contact here can be treated as an individual Hertz contact, uh, like this. And then you can basically come to a conclusion from doing these calculations that the area of real contact depends non-linearly on the applied normal force. So what Greenwood and Williamson did in 1966 was that in their theory, what they did, they had spherical bumps in their theory, but di- with Gaussian fluctuation of their heights. So the heights that have Gaussian distribution. So there is a random distribution of heights according to Gauss distribution, and they found from that, when they studied the contact, they found that the area is directly proportional to the force, normal force, but for very small loads. In 2000, in 2001, so these model Hertz and Greenwood Williamson models are what we call as asperity theories in contact mechanics. These are asperity theories. The um, Hertz model does not agree with experiments, because in experiments we say that the area of real contact depends on the normal force. This is the Coulomb's law. And here, but Hertz says that area of real contact is non-linearly dependent on the force, which is obviously not right. In 2001, Person introduced what they call as multi-scale contact mechanics, in which he found that the area of real contact is approximately proportional to the force, but for high loads. So the difference between Greenwood-Williamson and Parsons theory is that uh, Parsons theory agrees with experiments, and because here the relationship between uh, area and the normal load is valid up to 30% of the complete contact. So I will talk about why Greenwood-Williamson theory fails. Here, Greenwood-Williams theory fails because here, if you see there, if you see here, there is a asperity which is which is higher than other asperities. For example, this asperity is higher than the asperities which are nearby. So here, what happens when this asperity pushes on this elastic solid? What happens is in Greenwood Williamson, they don't take into account the elastic long range elastic deformation. This means that if this asperity pushes this elastic solid, uh, uh, then what should happen is the elastic solid, the asperities here lose contact, but because Greenwood Williamson does not consider long range elastic deformation, so they uh, and they treat uh, uh, each contact as a different contact. Uh, they are not able to give a correct theory, and I will show why. So there is what we call long range elastic deformation. So here what happens is if you don't take long range elastic deformation, then you will find more contact area. Uh, and if you consider uh, long range elastic deformation, you will find contact areas which are less. For example, here below, you will there is numerical study done by Professor Alcomvist and Professor Person, where uh, they used these both theories with long range elastic deformation and without long range elastic deformation, and they found that if you don't take into account long range elastic deformation, the contact area is higher. But in reality, if you take long range elastic deformation, contact area is lower. In these pictures, the blue is its contact, and the white is the non-contact. So, for example, uh, for, uh, if you predict the contact area wrong, what might go wrong? You might think, what will happen if I predict the contact area wrong? For example, if you take a static sealing application and suppose there is a fluid at high pressure here, and and there is a high pressure region here, and then there is a seal which has made contact contact which has this contact area distribution like this and like this. You will see that if the fluid starts because of the pressure difference between the sides of the contact, if the fluid starts moving, if you take long range elastic deformation, you will be able to predict correctly that the fluid will not leak here on the left side. But if you don't take long range elastic deformation, you will see on the right side, if the fluid starts flowing from here to from here to here to from the high pressure side to the low pressure side, the fluid will leak. So you cannot predict leakage with Greenwood Williamson uh, and other multi-asperity theories. So you have to take into account multi-scale contact nature of the theory, and also you have to take into account long range elastic deformation. So so what is Parsons theory? So briefly, I will describe what is Parsons theory. So every engineering surface that you see with the naked eye, it's smooth. So we can consider at the naked eye level, we can say that if you apply a normal force or pressure uniformly, then it will be same. It will be same uh, at the pressure at the interface. If we neglect friction, will also be the same. So this means that if you plot uh, stress distribution, probability stress distribution, you will have a Dirac delta function. This means that there is only one stress at a particular stress. The probability of finding that stress at the interface is very high, and it's a Dirac delta function. And delta function is very thin and infinitely high. So, and the area under the curve of this Dirac delta function is 1. So at the lowest magnification with the naked eye, we see that at the interface, you will have this you have will have at the interface the same stress that you apply. But you start magnifying this if you start, but in person's approach, you start magnifying this. You start magnifying the interface, and you will see that there are now areas where you will see there are no contacts, and then the areas where the asperities make contact, and then there are regions of high pressure, and then the non-contact areas will have a region of low pressure. So we'll see that the stress distribution at the interface now broadens, and this uh, now the non-contact the zero stress is also increasing, because you will have many different non-contacting areas. And when you further increase the magnification, you will see that a short wavelength surface reference appear, and they will they will broaden the stress probability distribution, and at the same time they will also increase the non-contact areas. So Parsons theory is able to predict this stress probability distribution for different magnifications. So he starts from full contact, and then he goes to basically no contact. Because when you start magnifying and magnifying, then you will see that there is very less contact. But then he has some he has introduced boundary conditions. So the in the so he this stress distribution is basically a diffusion type equation. In his theory, the stress distribution is a diffusion type equation in which the time is replaced by the magnification, and the spatial coordinates is uh, spatial coordinate is replaced by the interfacial stress. And then there is what we call the diffusion coefficient, which depends on the diffusion coefficient as a function of magnification. And this diffusion coefficient depends on the elastic properties of the solid and the surface roughness power spectrum. So the there are there are two boundary conditions. So the first boundary condition is that at uh, at the probability of finding zero stress at any magnification is 0. So you will see that the probability of finding zero stress at any magnification is 0, and 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 this is what we see here. And then he says that the stress there cannot be infinitely high stresses at the interface. So the probability of finding infinitely high stresses is 0. So you will see that uh, there are no infinitely high stresses. So was the case. So this is in red because this condition will change if we take adhesion into account. Now we have not taken adhesion into account. If we take adhesion into account, then we have to take uh, uh, how the tensile stresses at the contact edges, and that will change the formulation a bit. but not, so it will change the formulation a bit. So the initial condition is, you can see at the lowest magnification, you have a single stress. And this is what we see at the lowest magnification. This is the initial condition. So this is what we find, we get a Dirac delta function here, that at the lowest magnification, you have a single stress at the interface. When you plot, when you predict area of real contact as a function of load by using exact numerical simulation, which are done for very small systems, and using analytical Persons theory, you will see that they basically are valid up to 30% of the contact. That is, they are valid up to 30% of area of real contact. So at a upon a0, a is the area of real contact, a0 is the apparent area of contact. So so when this area of relative area of contact is 1, then there is full contact. So this means that high pressures, there is full contact, and there is a linearity between the pressure and contact area up to 30% of the load. And you can predict the area of real contact using this equation, which is an error function. Now I will briefly talk about how we use, we talk about rubber friction. I will talk about some basic theory, and then I will try to explain some experimental results. So rubber friction. So when you have a rubber which is sliding on a rough surface, that you have different contributions to friction. So the friction force is a combination of viscoelastic response, F visc, and then there is a force generated from the viscoelastic response, and then there is a force term which is due to adhesion. So in adhesion, so if you consider this as to be dry sliding, there is no lubricant present at the interface, then you will, this adhesive friction, adhesive contribution to the friction force is your shear stress, the shear stress times the area of real contact. So the adhesive friction basically arises because of the sharing of the area of real contact. And schematically, if you measure rubber friction as a function of velocity, you will find a blue curve, but which is a combination of two curves, which is mu cont and mu visc. So mu cont is nothing but the contribution from the adhesion, and it lies at low velocity, and lies at low velocities. Its maximum lies at low velocities. This means that it has a high contribution at low sliding velocities, because the rubber has time to bind with the surfaces. And viscoelastic contribution is basically pulse. So when you slide rubbers on a randomly rough surface, there are pulsating deformations that happen. And this pulsating deformation, because the pulsating deformations happen because there is a surface roughness present. So when you slide a rubber against, if you see here, if you slide a rubber on a surface with roughness, you will see there is large energy dissipation at the interface, because friction is a dissipative process. So basically friction happens fundamentally because it's a dissipative process. So dissipation of energy is required for friction to manifest. So when you move the rubber along the rough surface, the asperities will contribute to, the asperities will deform the rubber at different frequencies, and that will give different dissipational energies, and that will decide the friction. So there are many levels at which uh, 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 the energy dissipation takes place. And for short length scale, the energy dissipation is very high. But in Pearson's theory of contact mechanics, uh, according to Pearson's theory of contact mechanics, he says that you cannot exclude any length scale, because if you, you cannot exclude any length scale from calculating this energy uh, dissipation. You have to include all length scale. All length scales are important. So short length scales are short length scale here is as important as long length scales. If the ratio between the height, amplitude, and the uh, wavelength is same in both the cases, so they will have different contribution. So viscoelastic contribution in rubber friction can in a steady state in rubber friction in rubber in Pearson's contact mechanics theory can be calculated using this equation. The main point to note here is that to calculate the coefficient of friction, you just need a power spectrum of the surfaces and then the elastic properties of the solids. So there are two things that are important for calculating the friction of a rubber, uh, predicting the friction of rubber. That is the surface roughness power spectrum C of Q, and then the elastic properties of the rubber. So adhesive contribution, I say, as I have already said to you, that adhesive contribution happens because uh, at low velocities, what happens is you have polymer chains. This is a schematic and idealistic diagram. So what happens is you have chains on the elastomer surfaces which come in contact with the rough surface, and then they stick to the rough surface. And when you start to move, then these chains are stretched. These chains are stressed, and then when they are stressed long enough, then they will break the contact, and then they will release energy. And that energy is what is a fundamental reason of uh, how friction appears due to adhesion. So at low velocities, what happens? So there are at low velocities, what happens? There is a lot of time for the rubber molecules to bind to the surface, and the frictional shear stress or the adhesive contribution to friction is less, because here the rubbers are binding tightly to the substrate, and but you will see a bit of energy dissipation because of thermal fluctuations, which will basically break the bonds. So there are thermal fluctuation of order kT which can break bonds at low velocities. You will have low low adhesive contribution. But at high velocities, these rubber molecules don't have the time to bind with the substrate, and then what happens is they don't have enough time for binding, stretching, and releasing energy. So they have less contribution. The adhesive contribution is less. You can see that the frictional force due to adhesion, the adhesive frictional force can be calculated by the product of the area of real contact and the frictional shear stress from this equation here. So if you have an area of real contact and you have a shear stress, you can basically calculate uh, frictional force due to adhesion, which is basically coming from sharing the area of real contact. So the fundamental here is that the chains bind to the substrate, and then they when they when they start, so they perform stick slip type of motion, releasing energy which contributes to adhesive friction. There are many more contributions to area of the adhesive friction coefficient. Uh, they can be and this happens at the area of real contact. At the really at the area of real contact, there can be there can be you can shear a thin film, uh, which is a contamination film. Here in this figure there is a contamination film here. You can shear this film, and then there is a there is a uh, there is a dissipation in there also, energy dissipation here. If you consider the asperity and the rubber, if you move the rubber over an asperity, then you have some cracks at the edges, and that cracks, when they open up, they release energy, and that is also can contribute to the overall frictional force and the resultant uh, adhesive friction coefficient. And then there is also some, as I told you before, that rubbers have different fillers in them, and these fillers, they can scratch the surface of the substrate, and then that wear process, the scratching and plowing mechanisms by the filler particles on the substrates, can also be a cause of energy release. So that can also contribute to friction in the area of real contact. I will now talk about some experiments that we did here in Ulish. Here we in the lab here we have a friction freezer in which we can measure. We have a freezer which in which we inside which we have a surface of interest, substrate of interest, and then that substrate is driven by an electric motor with a gearbox. And then what we do is we load the substrate with the uh, a sample uh, whose friction coefficient is to be known, and then we start varying the velocity. So in our experimental setup, we can vary the velocity from 1 micrometer per second to 1 centimeter per second. And we can vary the temperature from minus 45 degrees Celsius to plus 20 degrees Celsius. So we can measure friction coefficient or friction force as a function of temperature and as a function of velocity. So what we do is basically we take us, this is the substrate that we used. This is a concrete surface with a randomly rough surface, randomly rough surface roughness. And here is the power spectrum of this concrete surface. And this contains all the information that is needed for doing analytical calculations using Parsons theory. So so a brief literature review I will give you to in order to understand the topic. So in 1963, there was a scientist called Gross. He carried out experiments he carried out friction experiment at different temperatures, and he got these raw data, like as indicated here. So he carried out experiments, he varied temperature, and he measured the friction as a function of velocity, and he did it at many temperatures. So you can see the raw data here. So what he did with these raw data is that he used bulk viscoelastic shift factors. In the earlier slide, I showed you an equation called as WLF equation. So what he did, the scientist Grosh, his brilliance was that he showed that these curves can be shifted by the same shift factors that govern the shift of the viscoelastic materials to form a master curve. So what he did, he shifted them with the same shift factors, and he obtained a friction master curve now. Instead of uh, with the same shift factors, he obtained a frictional master curve, and this showed for the first time that the friction is uh, uh, results from the energy dissipations taking place in the bulk of the rubber. So what we did in Ulish is we wanted to try to see if we can do the same sort of experiment that Grosh did in 1963 with with the current technology. So what we did, we repeated this. So we took a rubber compound, and we did the same thing. We measured friction coefficient at different temperatures at, with and we as a function of velocity. So for see, um, we measured from 20 degrees Celsius till minus 40 degrees Celsius. Uh, we measured friction coefficient as a function of velocity at different temperatures, and we got these curves. So when we use the bulk shift factors obtained from the viscoelastic data of this material, we are not able to form a smooth master curve as formed by Grosh. Here, Grosh is able to form smooth master curves, but we are not able to form smooth. We were not able to form smooth master curves. So what we did was we anyhow shifted the curves and we formed a smooth master curve. And then we realized that uh, the adhesive contribution to friction has a different temperature dependency than uh, than adhesive contribution to rubber friction has a different temperature dependency, in the sense that so if you see on the right, this green curve is what these are the shift factors that we get by using bulk viscoelastic shift factors. And this red curve is what we obtained when uh, uh, we formed a smooth master curve. Then we realized that the adhesive contribution to friction has a has a different temperature dependency than the bulk. So adhesive contribution basically takes place at the surface, and this is where the rubber patches they bind and then do cyclic stick slip. So it has a weaker temperature dependency as compared to the bulk of the rubber. So so why there is a weaker temperature dependency can be explained by the fact that when you have a rubber sliding on a hard substrate, there is a because of short wavelength surface roughness, there is a region of high chain mobility at the interface, and that has low energy barriers for the there is low energy barriers for segmental mobility at the interface between the rubber and the hard substrate at short length scales. So this is the main reason why we see a uh, we see it low activation energy here. For the adhesive friction, the activation energy, which is of the Arrhenius type, has an activation energy of 1 electron volts at the surface. But at the bulk, the segmental mobility to happen and for dissipation to happen, uh, the activation barrier energy is approximately 2 electron volts. So because of the free volume that is available at the interface between the short length scale uh, roughness and the rubber, you have this weaker dependency. Now I will talk briefly about sealing at low temperatures. So in 1986, NASA had sent they were doing some space mission called Challenger, and when what happened was they used and that Challenger mission basically failed, and that failed because people at that time uh, uh, were not aware or somehow ignored the fact that the o-ring that was used in the uh, in the rocket booster was basically it started to contract, and there was a leakage path that formed for the fuel, and the fuel leaked, and then the tragedy struck, and then the Challenger was basically the mission was uh, it was had a bad ending that many people died because of not uh, because of not properly understanding or ignoring the tribological aspect or the viscoelastic aspects of rubber. This tragedy happened. So there are many challenges in sealing at low temperatures. If you go in space, the temperature will decrease, and when you go up north in the earth, if you go up north, the temperature starts decreasing, and there are many machine components that use seals. For example, o-rings. So what happens when the temperature is below the glass transition temperature? So as I had already told you, below the glass transition temperature, the material has the polymer or the rubber has low segmental mobility, and it starts contracting. And when it starts contracting, because when it starts contracting, what happens is because of the different, so for example, here you take a rubber and you compress it, uh, but at low temperatures, this rubber will basically, because of contraction, uh, will contract, and it will lose the contact, uh, and that causes the seal to leak. So here, if you see the contact pressures that were calculated by simulations uh, by Akulichev, he showed that uh, as you decrease temperature, the contact pressure decreases. This means that the if you want to seal some fluid and the temperature decreases, the contact pressure is low. So the fluid pressure will overcome this contact pressure, and the fluid will start leaking. And uh, at low temperature, what happens is, for example, you see the figure here. Suppose you have an O-ring and you compress it at room temperature, and then you uh, you will form a leak path, and also what will happen is you will basically freeze in uh, elastic deformations. So rubber is the elastic deformation is is frozen in. So frozen in, and then that will also cause leakage. So if you see uh, force as a function of time, when the temperature is decreasing from ambient to below 40, you will see that as the temperature reaches from ambient to minus 45 and then it stays constant, the force that is keep holding uh, the two surfaces together goes to a minimum, and then goes to a minimum. There is, and then it breaks and the force becomes zero. This is what we call the adhesive bonds at the interface between the rubber and the counter surface steel will break, and then it will lead to a catastrophic leakage. So in Challenger disaster, this is what happened. So they loaded the seals, and then there were elastic deformations, and that elastic deformations basically frozen in frozen in elastic deformations coupled with thermal coefficient of thermal expansion mismatch. They all combined, and there was a leakage, and it was very catastrophic. I will talk about a bit on dynamic sealing systems. So dynamic sealing systems is where you have movement in the O-rings here. In the O-rings here, these are quasi-static systems. There is very least movement. But in dynamic systems, either it's reciprocating seal or it's rotary lip seals, you have movement. So there are many challenges. So for optimizing tribological performance, you have to optimize many things, because tribology, you have to optimize the system properties in tribology. So, so here you see that rotary lip seal is made up of rubber materials, and it has its own properties, viscoelastic properties. It has its own friction properties. It can age, and it has it's heterogeneous. So there are many variations in material properties. And then lubricant, you have to also optimize lubricant if you want a good sealing system which does not leak, gives low wear, does not leak, uh, gives low wear and low friction. You have to use good lubricant. So there are, in lubricant you can use grease, you can use oil, and then there are various additives in oils which have to be optimized for a particular oil, particular sealing system. And oils should be chosen such that the rubber material don't get degraded and don't lose their elasticity property. And then the environment, what is the temperature range you are looking at? If you want to seal at low temperatures or you want to seal at high temperatures, uh, uh, and harsh operating conditions, there is for example, oil and gas industries, there is demand of high temperature, high pressure sealing systems. And in automotive sector, you need seals which can last up to 25 years. And high lifetime is needed, low friction is needed, low wear is needed. So there are many requirements. So you have to optimize many properties like these. And then the design also plays an important role. So in this rotary lip seal, you can basically design your lip to have, because if you want low friction, then you have to design your lip in such a way that the area of real contact is a bit less, but at the same time not compromise on the leakage. And then you can have different patterns of seals, wave and helix, and different arrangements of these seals. And surface is also very important. You can, on the shaft on which rotary lip seal is sitting, can have different finishes, and that will also affect the properties. As we have seen that surfaces, the two surfaces and their surface roughness is very important. And then the operating conditions also pose a different threat, that there is dynamic runout or shaft to bore misalignments, and then the conditions of pressure, velocity, and temperature. So there are many things that will affect and pose a challenge to dynamic sealing systems. So basically, these seals, rotary lip seals, are used for retaining the lubricants, separating two media, have to seal under pressure, exclude dirt and moisture. So if these functions, these four functions have to, if you want to optimize and have all these four functions in a rotary lip seals, then you have to play with all these variables and many sub variables to really get an optimized tribological system for your application. So conclusions, we have seen that polymers are viscoelastic, and then their properties depend on time and temperature. And tribology is a system property. This means that you have to optimize the whole system in order for getting an optimal performance. And we saw that Parsons multi-scale contact mechanics is the state-of-art analytical theory in tribology for predicting rubber friction, stress probability distribution, interfacial separation, and area of real contact, which have many applications. And for Parsons theory of contact mechanics, you need only two uh, important quantities, that is the elastic properties of the solids and then the surface roughness power spectrum of the solids. So if you have these two properties, you can basically have predicting capabilities in tribology, which can, and these predicting capabilities can help you design your things, design your products better. So these are some list of some useful references that you can go through to get more understanding on the topic. I would like to thank my supervisor, Professor Person, for providing material for this presentation. Thank you. If you have any questions, please.
Thank you very much, sir. Dr. Avinash, that was an excellent presentation on starting with an introduction to brief introduction about polymers, then characteristics, especially mentioning those applications where how the things are going with this polymers. Thank you very much, sir. It's a very good presentation. Let's look for any questions. Actually, there were no questions in this question and answer session. Let us ask participants, if you have any queries, you may please post on question and answer. Hope, Dr. Avinash, there were no questions. Still, I can ask participants, if you have any questions, you may please post on our group. So that could be forwarded, the relevant questions would be forwarded to Dr. Avinash, and the things would be getting clarified, and we'll come back to you with proper answers as soon as we reach from the Dr. Avinash. No more questions. Thank you very much, sir, Avinash sir, for sparing your valuable time. So once again, on behalf of Geetham University and the Department of Mechanical Engineering, I would like to extend a heartfelt gratitudes to you. Thank you very much, sir. And today, I think everyone know, like we have reached the end of this 5-day international faculty development program on tribology. So I would like to, this is time has come like to propose vote of thanks. So before that, let me share my screen. Okay. Dr. Ashok, can you see this?
Yes, sir.
Yeah, that's good.
It is visible. You can go on.
Good, sir. Right. Now, this is a time to propose vote of thanks. I feel this as a honor for me to propose vote of thanks. I would like to thank each and every one of these speakers personally, and behalf of the Geetham, made this 5-day international faculty development program on tribology for reliability as a grand success. Starting with Professor Satish Vasu Kailas, he's a senior most professor from IISc Bangalore, has given a very good start with a talk started tribology. It starts at the surface and then question mark. So he has explained very elaborately the importance and why the tribology is required. So thank you very much to Professor Satish Vasu Kailas for giving a great start for this all 5 days faculty development program. So Professor Satish Vasu Kailas, on behalf of the Mechanical Department of Geetham University and the Geetham management, so we are extending a heartfelt gratitude to you, sir, and thanks for sparing your valuable time and providing us for other resource persons through your contacts. Thank you very much, sir. Then I would like to extend my gratitudes to Professor M.S. Bobji. He's a professor, has covered almost about roughness fundamentals, surface roughness fundamentals, given a very good and detailed information about the surface roughness fundamentals, where a researcher, what exactly looking for. There were some researchers having a lot of doubts how to do the things, how to characterize, what are the different methods. So hope like participants and researchers might got cleared all their doubts related to this surface roughness fundamentals. So on behalf of Geetham University and the organizing committee and the Department of Mechanical Engineering, I would like to extend heartfelt gratitudes to Professor M.S. Bobji. Bobji sir, thank you very much sir for being with us during this 5 days workshop. Then Professor Dr. Kathleen from University of Scotland, UK, has delivered a very nice lecture on coatings and lubrication for advanced applications, with a very good applications are being utilized in his research areas, like especially in aerospace industry and naval areas. So he has explained very nicely the coatings, different kinds of coatings, and how to characterize their coatings and how to test different methods. So he has very nicely explained and very clearly elaborated regarding the coatings and lubrication for advanced applications also. So on behalf of Geetham University and the organizing committee and the Department of Mechanical Engineering, I'd like to extend gratitudes to Dr. Kathleen for sparing his valuable time and being with us during these 5 days of faculty development program. Thank you, Dr. Kathleen, for your nice presentation and for sparing your valuable time towards this. Thank you, sir. Then Professor Anirudhan is a nice presentation with Professor Anirudhan has covered almost surface characterization. Many people are worrying about like how to characterize, what are the different methods, how can we overcome the difficulties, and how do we choose different methods, which method is going to be suitable for which kind of experiment. So almost all such things might have been cleared for the researchers and as well as for students. Dr. Anirudhan has given very good inputs to the researchers and participants regarding the surface characterization. Thank you very much, sir. Professor Anirudhan. Again, I would like to extend heartfelt gratitudes from Geetham University and the Department of Mechanical Engineering and the organizing committee. Thank you, sir. Professor Anirudhan, thank you very much. Professor Dr. Tej Singh. Dr. Tej Singh from Hungary has given very detailed lecture on potential of waste and natural resources in sustainable industry products. So professor has explained very widely about the potential of waste and natural resources in industrial applications. Hope almost all participants, those who are working in these areas, might have enlightened with his ideas and thoughts. That was a very nice presentation from Professor Dr. Tej Singh. So on behalf of Geetham University, we extend our gratitudes to Professor Dr. Tej Singh for being with us for this tenure of 5 days of International Faculty Development Program. Thank you, sir, Professor Tej Singh. Thanks for being with us during this International Faculty Development Program. Again, once again, from on behalf of the Department of Mechanical Engineering and Geetham University, I extend gratitudes to Professor Tej Singh. Thank you, sir. Thanks a lot. Then next, we have a renowned professor from Saudi Arabia, Professor Dr. Abdul Samad Muhammad. So Professor Abdul Samad has given a very good presentation on surface modifications for tribology, tribological solutions from nano to macro scores. So that was a very nice presentation from Professor Abdul, has given very clear and explained the different methods where surface modifications in tribological aspects from nano to macro has been explained very neatly with various applications, where many of us are not aware like what are these different applications where we could use all these things. So that was very elaborately explained by Professor Abdul Samad. So on behalf of Geetham University and the Department of Mechanical Engineering, I would like to extend gratitudes to Professor Dr. Abdul Samad Muhammad. Thank you very much, sir, Professor Abdul, for being with us during these 5 days of International Faculty Development Program. Thank you, sir. Then we have Dr. Avinash Tiwari. Just now we had a very pleasant and detailed lecture on polymers, started with the polymers and applications of tribological applications, and has been very neatly and keenly explained by Dr. Avinash Tiwari. Thank you, sir, Dr. Avinash Tiwari. So our 5 days faculty development program has ended with your enlightenment of polymers and its applications. That was a very nice presentation, Dr. Tiwari. So we are very happy to be here with us, and given a very good knowledge and inputs to the students and those who are working on especially polymers. And now maybe I guess researchers working on applications of polymers are being enlightened with various applications that you have highlighted in your presentation. That was very nice, sir. Thank you very much, sir, Avinash Tiwari, and for being with us to make this faculty development program as a grand success. Thank you, sir. Once again, on behalf of Geetham University Management and the Department of Mechanical Engineering, I would like to express my heartfelt gratitude to Dr. Tiwari. Thank you, sir. Thank you very much. And Dr. Ajay Kumar, we have in the morning session, spoke about tribology of metal matrix composites. So it was a very hot topic. It's been a long time. People are working wide areas of this metal matrix composites. Like majority of the researchers are working on these metal matrix composites. Dr. Ajay has given a very good inputs for the characterization of these metal matrix composites and its applications. How do the properties are varying with respect to the other properties? That was a nice presentation, and elaborated presentation has been delivered by Dr. Ajay Kumar. Thank you very much, sir. Dr. Ajay Kumar, on behalf of the Department of Mechanical Engineering and the management of Geetham University, we extend gratitudes to Dr. Ajay. Thank you very much, sir. And Dr. Amlankar, Dr. Amlankar has presented on a low temperature deformation of titanium and tool materials interface in dissimilar friction stir welding. He has given a very wide explanation on the concept of friction stir welding and application, and especially in a low temperature deformation in case of interface in dissimilar materials. So that was a very nice presentation with Dr. Amlankar. He's from IIT Dhanbad, has given very good presentation, and we feel happy for this presentation. I'd like to extend heartfelt gratitude to Dr. Amlankar for being with us during this 5 days International Faculty Development Program. Once again, on behalf of Geetham University and the Department of Mechanical Engineering, thank you, sir. Thank you very much, sir, Dr. Amlankar. Then we have Professor Dr. TVV Ellen Rao. So Professor TVV Ellen Rao has given a wide lecture on analysis of surface porous layer configurations in bearings. So it's configurations in bearings. So sir has also delivered a very good lecture on analysis of surface porous layer configurations. So hope this would help a lot for the people, those are working on different bearing applications, especially journal bearings. He has highlighted very good applications and shown the characterization of materials very neatly and very elaborately. Thank you very much, sir, Professor TVV Ellen Rao, once again from the Department of Mechanical Engineering and the management of Geetham University. I would like to extend heartfelt gratitudes to Professor TVV Ellen Rao. Thank you, sir. Thank you so much. And we have a last but not least, Dr. Jitendra Kumar Katiyar from SRM Institute of Science and Technology. From same Dr. TVV Ellen Rao sir has also given. So Dr. Jitendra Kumar Katiyar has given a very good presentation on tribomechanical study of solid fillers reinforced friction materials. So that was a very good explanation, has given a very good inputs on a tribological aspects of different friction materials. Sir has highlighted and given a wide explanation with various applications. Hope this would have been enjoyed by most of the participants and researchers working on this area. So it was a very nice presentation, Professor Jitendra Kumar Katiyar. Thank you very much, sir, once again on behalf of Geetham University and the Department of Mechanical Engineering. So we extend gratitudes to Professor Jitendra Kumar Katiyar. Thank you, sir. Thank you so much. So it was collective thanks from Geetham University and especially from our organizing committee to all speakers are being presented over here and have spent their valuable time in presenting their knowledge and sharing their knowledge and giving inputs to the participants. As a whole, we would like to extend our thanks to all speakers, and we wish we want you to join in the forthcoming events that we are about to conduct. So we want to have you in our forthcoming events. So thank you very much to you all. And we have The program started with our director, Geetam School of Technology, Professor Dinesh Seth. So he basically belongs to the Department of Mechanical Engineering. So he has given a very good introductory note on tribology and various applications and explained the basic concepts of tribology also. So I would like to extend on behalf of Mechanical Engineering Department and Geetam University, and especially from the organizing committee, a heartfelt thanks to Professor Dinesh Seth. Without his encouragement, this would have not been successful. So he regularly and continuously used to encourage us to go for this kind of faculty development programs on the latest trending topics. So thank you very much, sir. Professor Dinesh, thank you. Thanks a lot, sir. And we have our head of the Department of Mechanical Engineering, Professor T. Nageswara, sir. So Professor T. Nageswara always encourages and motivates to go for latest trending topics, and he always encourages to conduct this sort of seminars and webinars. Without his encouragement and motivation, this would have not a successful one. So I wish to thank Professor T. Nageswara, head of the department, has given on the first day, he has also given a keynote and a brief note on importance of tribology and highlighted the various features and courses and regarding convey the information about the university and various campuses. So this is my heartfelt gratitudes to Professor T. Nageswara for giving a very good start at the beginning of this 5 days International Faculty Development Program. Thank you very much, sir. Thank you, Professor T. Nageswara, sir. And I thank our management for continuous encouragement. So our management continuously encourages us to conduct this sort of events and conferences. So I would like to extend on behalf of the Department of Mechanical Engineering, Geetam School of Technology, especially from the organizing committee, to a great thank to our management for the continuous encouragement. Thanks to Geetam University for being with us every time. Then I would like to extend my thanks to all participants being with us during all these 5 days of tenure, attending these sessions regularly without fail, and which includes almost some professors and research associates and research scholars and fresh researchers, and not least, we also have students of our engineering college also. I wish to extend my heartfelt gratitudes to each and every participant who has been with us during these all 5 days of workshop. And I would like to extend my sincere thanks to all my panelists, Dr. Sandeep and Dr. Ashok Raj, and for being with us and making this event as a grand success. And we also have a faculty members. So I would like to extend a great thanks to all my faculty members of the Department of Mechanical Engineering for their continuous support and encouraging us to conduct this sort of events. Thanks to all my faculty members and all panelists, Ashok Raj and Dr. Sandeep. Last but not least, I would like to extend my heartfelt thanks to our organizing, technical organizing department, which is CATS department, we call as. So I would like to extend my gratitudes on behalf of the department and as well as School of Technology, and especially from the organizing committee to our IT department for providing these technical facilities during this pandemic. Like anyway, we are habituated to conduct these online events and all. Even then we faced here and there little technical problems. Even then they made this program as a grand success. So I'd like to extend my thanks to our Geetam CATS department, especially the people, those who cooperated. By name, if I say like the Harish Guru, the person in charge, Harish Guru, and one more person from the CATS department, Geetam University, Mr. Venkatesh, who have been with us during all these 5 days, taken lots of pains to organize all these things. Thank you very much. Thanks to you all. And thanks one and all. Now I would like to take a leave. So it was a very great experience with all these speakers and the sessions and all. People have ignited their, I think people have already ignited their research activities. So with these all inputs we got from various keynote speakers. Thank you very much, sir. Thanks a lot. Now I wish to extend.
Thank you, sir. Thank you, Rajshekhar, sir.
Thank you.
One more thing. We got to thank special thank you got to give to tell to Dr. Jitendra Kumar.
Jitendra Kumar, sir. Yeah. You please, sir.
Because he only
Ashok, sir. You may please.
So thank you very much, sir, Dr. Jitendra Kumar, and who initiate this program, and who motivate me to do the program. All credit will go to him, and my colleague Rashekar and Sandeep both help to conduct this program. Without them, I don't know how it will be succeed. So I thank, especially thank for Rashekar sir and Sandeep both, as well as our management, Gita management, and director of our institute and head of the department, and our faculty members, all who are supporting for everything, sharing all the detail, especially for others, Sandeep. And so thank you, one and all. Thank you
Thank
very
you,
much.
Ashok. Thank you. Thank you very much. Now I should convey a special thanks to Dr. Ajay for, sorry, Dr. Ashok for initiating these programs, initiation of this program. It's initiated with Dr. Ashok, and God gathered all you people, resource persons over here. So thanks to Dr. Ashok. And last, like I would like to have listen some participants. I want to have some feedback with the participants, how they have enjoyed these 5 days uh, International Faculty Development Program. Now, among the participants, I would like to convey special thanks to Professor Pradeep Radhakrishnan. He's like a professor from our medical college, very curious and eager to learn something from our mechanical field. So I thank Professor Pradeep Radhakrishnan. And we have one more person, like remember, usually posing questions like Dr. TCH Anil Kumar used to ask good questions. So that was a very nice interaction with the resource persons for getting their doubts clarified. Now, I wish like if any participant is there, would like to share their feedback for this 5 days International Faculty Development Program. Is there anyone can? Yeah, I got one person. CH Anil Kumar, sir. Sir, you can speak, sir. Dr. CH Anil Kumar.
Thank you, Rajshekar sir.
Thank you very much.
Sir, that's a very nice program you have set for us. See, from the pandemic time onwards, I have attended so many FWs.
Yeah.
And from day one onwards, seeing there is no program related to the tribological aspects, especially.
Yes, sir.
So actually, I wish to conduct this program, but when I seen this that this program being organized by your Geetham University, I felt very happy because
Thank you, sir.
there are so many FDP programs related to materials, experimentation, composites, AI, robotics, all these sort of things. But nobody has talked about the importance of the tribology, where we have surface interactions, where most of the energy and power losses are associated due to the tribological problems. So the importance of this topic is very high in the aspect of industries and the economy also. So I wish and I enjoyed each and every session from the day one session, which has given a brief introduction to the fundamentals of tribology, and session by session related to each and every aspect, every area, especially that even that civil side applications also, how the composites which are used for rubber waste material, how we can
Yes.
improve the tribological aspects, and that lecture by Professor yesterday's lecture, which he has told about that how the cryo turning, how we can improve
Yes,
the
sir.
tool life. So I enjoyed each and every session, and
Very nice, sir.
speakers, especially thankful to the speakers who has given deliberate, who has given extensive answers to the replies of the queries we have asked them, relatively whatever may be the time and how much the session is extended. So they with the same energy they have cleared our queries also. So which I didn't seen a lot in the other FDP programs. So I am congratulating the mechanical department of Geetham Bengaluru for organizing such a successful event, international FDP program on tribology for
Thank you, sir.
reliability. Thank you very much, sir. And
Thank you, sir.
I'm also thankful that you have made me as a participant. You have taken my candidature. I am very much thankful, sir.
Thank you, sir. That's a nice hearing from you. Thanks a lot, sir. Now we got one more participant who would like to speak. Maybe it's a student. Hello? 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 Hello, can you speak? Maybe you lost the connection or something. Hello? 1024. Can you speak? Oh, maybe something wrong. Anyway, that was very nice. Like, we have come to the end of the program. So you can see like the cover page of the program we have. So we wish like we would have this kind of programs in future also. And right. So there's a not least, I would like to thank all our organizing committee, starting with our chief patrons, Mr. M. Sri Bharat. He's a president of Geetam University. Thank you very much, sir. Professor K. Ramakrishna Rao, a chancellor of our university, for his continuous support and encouragement. Thank you very much, Professor. And we have a patrons, Professor K. Sivaramakrishna, vice chancellor. He is also our continuous motivator to conduct this kind of faculty development programs on the latest trends. Thank you to the Vice Chancellor, sir, and thanks to our Registrar for his continuous support and encouragement, especially. Thank you to Registrar, sir. And we have a co-patrons, Professor Sailendra Dasari, sir. Thanks for, he's a campus in charge. He always motivates us in doing this sort of things. Thank you. It's my special thanks to our Professor Sailendra Dasari and Professor Dinesh, the director of the Geetam School of Technology. Thank you very much, sir. Professor K. Srinivas, principal of our School of Science, always motivates us in doing this kind of events. Thank you to Professor K. Srinivas and our director, administration and admissions. He always motivates and keeps on forcing us, do the activities. So without his support, this would have not made possible. Like, a special thanks to Sri Vamsi Datla, director. Thank you, sir, Vamsi sir. And my head of the department, Professor T. Nageswar Rao, he is behind us always for this sort of events to conduct. Special thanks to my HOD, Professor T. Nageswar sir. So thank you very much. Thanks one and all. So if
one more thing, sir, we forgot to add our Pro VC sir name. Please.
Sailendra Dasri sir, and my special thanks to our Pro Vice Chancellor,
Professor D.S. Rao.
Professor D.S. Rao sir joined us recently to strengthen our School of Technology as well as the other schools also. So I would like to extend my special thanks to Professor D.S. Rao for giving us continuous support and motivating us in conducting this kind of events. Thank you very much, sir. Pro VC sir, thank you very much. Thanks a lot. Dr. Ashok, would you like to speak? And we got another panelist, Dr. Sandeep. Sandeep sir, would you like to speak anything?
Yeah, thank you. Thank you very much to all my colleagues, to all the panelists, to all the guests who have come for a elaborate and enlightened knowledge sharing platform. Thank you for everything. And we wish to continue this, and we wish to have more such webinars on much more topics soon. And we wish your cooperation from all the attendees so that we may have further successful seminars. Thank you. Thank you all.
Thank you very much, Sandeep. So I would like to thanks once again for all our organizing committee and our participant and guest and our panelist and host and CARES department and all, one and all. So thank you very much, guys.